So welcome to this lecture of digital electronics EI-207. In this lecture we will discuss about the design of synchronous counters. Synchronous counters are also called the parallel counters. So in the last lecture we have discussed about the various type of counters, that is the asynchronous and the synchronous counters, basic definition, and then we have discussed in detail the asynchronous counters. Now here we will start with the synchronous counters. So synchronous counters are the counters in which all the flip-flops are triggered simultaneously by the clock. Whereas in the asynchronous counter, we have seen already that the first flip-flop triggers the second flip-flop, and then the second flip-flop triggers the third flip-flop, and so on and so forth. The chain continues. Whereas in the synchronous flip-flops, synchronous counters, all the flip-flops are triggered simultaneously. That is, all the flip-flop gets the clock pulse simultaneously. So that is an easy thing, but the thing is, like this type of flip-flops, in this type of flip-flops, we have to design the circuit, because in this type of flip-flops we don't give the output of the first flip-flop. We do not connect the output of the first flip-flop to the input of the clock input of the second flip-flop, as we did in the asynchronous counter. What we do here is, rather than connecting the output of the first flip-flop directly to the input of the second flip-flop, sometimes we may have to connect some in between some we have to connect some combinational circuit to get the proper function. So that is why this type of synchronous counters are little complex to design. Whereas as all the flip-flops of the counter gets the clock pulse simultaneously, so these flip-flops are fast. Okay. So whenever we have to design a synchronous counter, we have to start with, let's say, first of all, we have to choose that we want to design the counter with the help of which type of flip-flop. So if it is already mentioned and you have the availability of the flip-flop, then you can use that flip-flop. But if there is a restriction that only a particular flip-flop is available, or somewhere it is written that you have to implement that flip-flop with a certain type of flip-flop only, this counter with a certain type of flip-flop, then there is no option and we have to choose that flip-flop. Okay. Otherwise, so first step is to choose the flip-flop. So by which flip-flop you want to realize the counter. Then we have to also choose that how many counts we have to do. So depending upon how many counts you want, we choose that how many flip-flops will be required. So we decide that how many number of flip-flops will be required depending upon how many counts we have to do. Okay, how many counts are required. So the logic is same as what we have discussed in our asynchronous counters. So we have to see that the count which we actually want to count should be less than equal to 2 to the power of small n. So as small n is here the number of flip-flops. Okay. So this we already know that how to use this equation, n, capital N, less than equal to 2 to the power small n. So how to use this equation, and using this equation how to decide the number of flip-flops, we have already discussed in our last class. Now after this, as I have told you that we have to decide what should be connected on the input of a flip-flop in this case, in case of synchronous counters. So we need to write the first we need to write the state diagram, and then we need to write the excitation table and the state table for a particular flip-flop. Okay, in terms of the present state, next state, and its input. So what inputs it will get. So excitation table when you write, so you understand that what does it mean. Okay. So first you write the state diagram. With the help of state diagram, we mention that how whatever is given or whatever we understood by the design problem is pictorially drawn on a diagram. So that diagram which depicts the transition of states, the transition of the circuit from one state to another state is called the state diagram of for that particular problem. So we have to draw the state diagram for the problem. So by drawing the state diagram, it becomes very clear and if we make any mistake, we can refer that state diagram and can correct our mistake. So this we will understand the whole procedure. We'll understand with the help of certain examples. But let me first give you the general procedure, that what is this, and then we will continue with that also. So first we write the state diagram, then we write its excitation table and the state transition table. Okay, using the first you write the state diagram, and then you can write the state table as well. Okay, so state table shows you whatever you have written in the state diagram, you can write it in the state transition table, and then from that transition table obtain the excitation table, okay, for any particular flip-flops in terms of present state and the next state. Then write the, okay, so this we have done already. Then by this after writing the state transition table, what we can do is we can so first you write this, then you write the state transition table by using the excitation table. Okay, then what we do is we use the state table to simplify the logic. Okay, so for every input, how this input should be designed, which gates should be used to realize that particular function. Okay, so that we decide by the help of our Boolean expression. So the Boolean expression is obtained by simplifying the logic for each of the input, and that is done by the help of K-maps. Okay, and then later on we draw the logic diagram with the help of that equation, whatever we have drawn, and whatever we have obtained by after simplifying the K-map. And along with that we use our flip-flops. Okay, so this way, by using all this whatever we have done so far, we draw its logic diagram, and hence we obtain the circuit for the counter. Okay, so this we will understand with the help of certain examples. I might have made some mistake here in the previous slide, so I felt it. Okay, so if I made any mistake, so please correct it, and we will understand it with the help of example also. So please clarify that with the help of example also. So this design, let's say we have to design a mod 4 synchronous up counter using JK flip-flop. Okay, so it is only a up counter. So I'll give you a certain simple examples, but later on you can understand, or you can use these examples to realize various difficult problems from the book as well. Okay, so you can try the questions from the book by your own. After having the basic understanding of the synchronous counters, now you will be ready to solve all the problems, I think. Okay, so you see, let's suppose we have to design a mod 4 synchronous up counter using JK flip-flop. So you know what is mod 4. So mod 4 means the counter should be able to count up to 4. Okay, so not up to 4, it should count 4 states. So if it is counting 4 states, so then the count should go from 0 to 3, right? So the counter, and we know using our equation, so capital N should be less than equal to 2 to the power small n. So using that equation, if we decide, so our small n will come 2. Okay, so we have to use 2 flip-flops. So number of flip-flops you have decided, and the type of flip-flop is also given, which is JK flip-flop. So no problem. Now we know that from the statement of the problem that we have to design a synchronous up counter. So up counter, by using this statement up counter, we can draw its state transition table. Okay, so state transition diagram, or you can call it state diagram as well. So what is it? It shows you the state in which the circuit will go. Okay, so the circuit will move in these states. So starting from the 0, if the circuit starts from the 0 state, so we'll assume that or otherwise what we have to do is we clear all these states before applying the first clock pulse. So first we clear the states, okay, the current states, and then we apply the first clock pulse. So if all the states are clear, then the counter is in 0 state. Then from that state, if you apply the first clock pulse, then the circuit should move on to the next state, and that state should be called as 1. Okay, then it moves on to on the appearance of the second clock pulse, it moves on to the second state, which is 2. It should count 2, and then later on it should move in the state 3, and when the fourth clock pulse appears, then it should move again to the initial state, 0 state, and it should keep on repeating these states. So if the circuit do this, is capable to do this, then it is called a mod 4 counter. And if in the if whatever flip-flops you are using, if they are all clocked simultaneously, then it will be called synchronous up counter. Okay, so in binary forms, if I represent the same equation, same state diagram, so it can be written like this as well. So usually in the next slides you will see, in next few problems, or in the book also, you will see that the state diagram is written either in this form or either in this form. So you can understand it very easily that the same state diagram which was written in decimal equivalents is now written in binary equivalents. Okay. So after writing the state diagram, then the third step is write the excitation table. So here the problem given is the JK flip-flop. So for the JK flip-flop, we will write the excitation table. So from our discussion of the flip-flops, we know that the excitation table of the JK flip-flop is something like this. And this excitation table is written in terms of the present state, next state, and the inputs. So we have to determine what inputs we have to give if we want the present state to move to the next state. Okay, so whatever is our present state and we want some predefined standard next step, then we have to connect the inputs to this particular combination. So we already know. So using this state table and our mod 4 state table, we can write. So what is this table? So our counter, let's say, is in the present state. Okay, then the next state should be this. So if it is in the 00 state, from the state diagram we know that if the counter is in the 00 state, the next count should be, so this is your MSB and this is B is your MSB and A is your LSB here. So you know that if the counter is in the present state 00, so on the appearance of the first clock pulse, the counter should move to the next state 01. Okay, if it is in the present state 01, it should move to the next state 10. Then if it is in 10 state, it should move to 11, and if it is in 11, it should move to again to the 00 state, the initial state. Okay, so this is what your present and next state looks like. So corresponding to this, you can see that if this is your present state for A and this is your next state for A, so then what you have to apply is the input. Okay, so if this is your present state and this is your next state, you can see that present state and next state. Okay, for the JK flip-flop you want. So if this is your present state and this is your next state, you can see that what inputs you have to apply. So if I just consider the A input, and if I say that if A is like 0 here in the present state and A should be 1 in the next state, then for this particular we have to decide the inputs J and K, because you see we are using two flip-flops. So each of this is a JK flip-flop. So we have to decide the inputs for each of them. Okay, so that is why I have said that for A flip-flop we have to consider the present and next state for A flip-flop first, and then for the B flip-flop, or you can use the otherwise also. Okay, you can do vice versa as well. So if you take the case of A, then we know from this state table that if your A is presently 0 and you want it to be 1, then you see what should be your case. If it is 0 and you want it to be 1, then your J should be 1 and K should be X. So you see J is 1 and K is X. Similarly, if you choose any other state, you can match it with this table, and you can, from this table you can write this particular this J and K. Similarly, if you want to check whether, if the present state is 0 in B of B and you want the next state of B to be same as 0, then what should be your combinations? So you can see that J should be connected to 0 and K should be connected to anything. Okay, either 0 or 1. So this is what we have done. So on the same lines, you can fill the other entries of this table. So if you do this, then you get the state table for the mod 4 counter. Okay, so this is a simple example which I have taken to explain you the process, and then later on using the same process you can do any other example. Okay, so you see, now after doing this, what we will do is we will simplify the Boolean expression. We will find the Boolean expression that how this JA, KA and JB and KB should get the connection. Okay, if there is some if there is direct connection from J to from flip-flop A to B, okay, so that can also be found, or if it is some or if it is in between there is some gates which you are using to get particular functionality, then that will also come if you write the K-map for this. So what you have to do is we have to simplify each of this input. Okay, so you can see that there are 4 inputs, JAKA and JBKB. So for each of this input we have to write the K-map in terms of the present state. Okay, so you see our present state is, let's say, 00, 01. Okay, so you see this is the K-map for your, because there are 2 variables only, so I have used 2 two variable K map. So for JB, JB, so this is your MSB. So if you use this JB, if you write the K map for JB, then you can see that the K map will look something like this, because I have written it in terms of present state. So 0, 0 is the present state. So this is your cell. For this, output is JB is equal to 0. For this state 0, 1, which is this, B is equal to 0 and A is equal to 1. So B is equal to 0 in this cell and A is equal to 1 in this cell. So for this cell, your JB is equal to 1. So this is what I have filled. For the other two cases, when B is equal to 1 and A is equal to first 0 and 1, so A is equal to 0 here and A is equal to 1 here, and B is 1 in both the cells. So then you can see that for both the cells, they are cross. Okay, so don't care conditions. So now if you group them together, then we can see, if we group them together, then we see that JB will be equal to A. Okay, so whatever output flip-flop A is producing, okay, that will go directly to the J input of the B flip-flop. Okay, so this is what it means. Now similarly, on the same lines, we can write the K map for KB as well. So this is the K map for KB, and if we group this two, if we form a pair for this terms, then we get KB is equal to A. Okay, so JB and KB both are getting same value. Okay, A. That is, the output of the first flip-flop is fed to the inputs of the second flip-flop, to both the inputs of the second flip-flop. Okay, J and K. Okay, whereas for the first flip-flop, if I write for the LSB flip-flop, then you can see that JA, because all these entries are because if these two are don't care from this table, if you'll see JA, so if these two entries are don't care, then you can form a quad with this, and JA will be equal to 1. Similarly, if you form this for KA, so it will be 1 in this case. Okay, so this is how we find the equations. So we find JB is equal to A, KB is equal to A, which means they are connected together. J is equal to 1 and K is also equal to 1. So which means these two are also connected together. So considering this, if I draw the circuit diagram, then you can see that the circuit diagram will look, well, the logic diagram for the counter, for the synchronous up counter, okay, a 2-bit synchronous up counter will look something like this. So the circuit will look like, see, this is your clock pulse. So this is an H trigger, and it is a positive H trigger because we are not using any bubble here. So positive H trigger, and you can see that this is a triangle is here, so it is a H trigger. So this is our flip flop JK, A flip flop LSB, and this is our MSB flip flop. So the clock pulse is connected simultaneously to both the flip flops. Okay, so you see this clock pulse is going to this A flip flop, and the same clock pulse is coming to the B flip flop also. So the clock pulse are simultaneously connected to both the flip flops. That is why it is a synchronous counter. Okay. Now whatever we have done whatever we have done in the last few slides, we found that JA. So this is our A flip flop. So this is our JA and this is our KA. So both of them should be connected to the high voltage, which is equal to 1. So we have connected it to VDD, the supply voltage, or the logical 1, whatever you can say it. Okay. So it is a sort of 5 volt. Okay. So if I assume that 5 volt is considered as high and 0 volt is considered as low, so then VDD will be equal to 5 volt here. Okay. So this is logically connected to 1. So now whatever it is coming here, so that let me call it A or QA. So here it will be QA bar. Okay. So we don't have to use QA bar. We'll just use QA, and this QA, from this equation we find that QA or J, see this A. Okay, so A is nothing but our QA, so output of our first flip flop. So this is what it is. So this is becoming the input for the second flip flop, and which is JB input. So JB is directly connected. That is why JB is directly connected to QA. Okay, so this is QA. You can write it QA or QA. Okay, so this is A. In short, I have written it as A rather than QA. You can write it as QA as well. And this is your QB. Okay, and this both the inputs, as we know that both of them are 1 1. So that is why it is connected to VDD. And as we know that both these inputs are connected to A, so that is why J and K are tied together, and both of them are connected to the output of the first flip flop. So with this, we see that how we can realize or how we can implement a synchronous counter. Okay, so this was a simple example to realize a 2-bit counter. Now let us see another example. Okay, so same procedure will follow for any counter. Okay, so in this case we have used all these states, but somewhere we may not use all these states. So whatever we have done in the discussion of the asynchronous counter, same logic you can apply here. You can write the state diagram, state table, and for those states where it is not becoming for those invalid states, we can consider those invalid states as don't care and can design the circuit accordingly. Okay, so that we will see later on if time permits, or like we'll see this. So let's say we want to design a 3-bit up down counter. So 3-bit up down counter is like 3 bits. So the number of flip flops which we have to use is 3. So if the question is something like as given as 3-bit, so you know that the number of flip flops will be 3. So this 3 flip flop can count how many number of states. So to find that, you have to write 2 to the power 3. So 2 to the power 3 is equal to 8. Okay, so this counter which will make with the use of 3 flip flops, which is a 3-bit synchronous counter, and you want to count a up down counter. So here what we want is, we want to make a circuit which can simultaneously count up as well as down. So depending upon some particular control input, so if that control input or the mod input if you call it, so if it is in the up counting mode, if the counter is in the up counting mode, then it should count in the upward direction, starting from the 0, then 1, then 2, then 3, okay, up to 7. And if it is in the down mode, okay, if you put the counter in the down mode, then it should count in the reverse direction, starting from the 8, 7, 6, okay, so like this it should count. Okay, so this is what it should be. So there should be some other function, other terminal should be there which can control the mod of the circuit, okay, or the mod of the counter as well. So you know that the number of counts which you can count with this counter in one mod is 8. Okay, so you see, so in both the mods it can count 16 counts. Okay, so as I have told you that to control the up mod and the down mode, we have to use a mode control input, or let's say name it as M. Okay, so M input we have to use for up and down control. So M is equal to 1 for up count. So let's say if in our circuit M is equal to 1, it counts in the upward direction. Okay, and if our M is equal to 0, then it should count in the down count. You can decide it in the opposite way also, but let's say if I assume that for my circuit, for when M is equal to 1, it will count in the upward direction, and if M is equal to 0, it should count in the downward direction. So if I decide this, then I have to design the circuit accordingly. So let's start with, okay, this circuit I have shown here, but we'll see this in detail later on. Okay, so let's see. Okay, start. So forget this circuit okay, so just forget this circuit for time being, don't see it here. Okay, assume that it is not here, and we'll come back to this particular circuit later on. So you see, just because to save space, I have placed it here to show everything in one slide. Okay, so let's say we want to design this 3-bit synchronous up down counter. So we have decided that we have to use, so it is given already in the previous slide that we have to design it with the JK flip flop. So type of flip flop is given. We have also decided 3-bit synchronous counter. So we know that 3 number of flip flops will be required. We have decided that it can count up to 8 in one direction in one mode, and 8 in the other mode. So total 16 counts it can count. So for in counting in one direction, M should be equal to 1. In counting in other direction, M should be equal to 0. So this we have done. So let's say count up when mod signal M is equal to 1 and count down when M is equal to 0. So let's say we design first the up counter. We can design them in different ways. So here I have taken a simpler way in which first we will design an up counter, then later on we will design a down counter, and in the third step we will mix them up together. Okay, so or otherwise you can do it in the other way also, but that will be little complicated to understand in the very beginning. So that is why I have considered this procedure to explain you the things. So let's suppose I want to design a up counter only, which can count from 0 up to 7. Okay, so from 0 to 111. So 8 counts are there. From 0 to 7, you will see there will be 8 counts. So this is the state diagram. So let's say first we draw the state diagram for this. So if we draw the state diagram, then your counter is in, let's say, 0 0 state. So on the appearance of the first clock pulse, Okay, it should move on to this state, then this state. So 0 0 0 0 0 1, then 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So in all you can see there are 8 states. So when your m is equal to 1, the counter should count in all this, should go into all these states. Okay, and should, when it goes into all these states, you say that the counter is counting there's all counts, okay, all these states. So starting from the 0 0 0 and 1 1 1, when it finishes in the 1 1 1, it have 8 counts. So considering this state diagram, you can write its state table. So let me magnify it a little bit, okay, enlarge it so that you can see it easily, because this diagram you don't have to see, this logic diagram you don't have to see, so I won't show it here. And let's see this excitation table here. So considering this logic diagram, we can write its excitation table. So excitation table is your present state. Okay, so this is like next state, okay, not the present state. So this is your present state, this is next state, and these are the required excitation to move the circuit from present state to next state. So if your present state is 0 0 1, so this is your LSB and this is your MSB. So if the circuit is in the present state, this present state, and you want to move it to the next state, this next state, then you have to apply this as your input. Here I have not used the excitation table of the JK flip-flop, that you can refer from your previous slide. Okay, so in the previous discussion we have seen that how the excitation table looks like for a JK flip-flop, so you can use the same excitation table here. If it would have been a different flip-flop, then I should have written the excitation table for that, but I am using the same JK flip-flop, so I have not repeated it here. So here you can see that using the same JK flip-flop excitation table, we can see that when Q1 moves from present state to the next state, these are the inputs we have to apply on the first flip-flop J1 and K1. When Q2 moves from present state to the next state of Q2, then these are the inputs which we have to apply on the J2 and K2. Okay, whereas when Q3 moves from present state to the next state, then these are the inputs we have to apply on J3 and K3. Okay, so this is what we know. Now after doing this, after writing the excitation table from the state diagram or otherwise, you can see, then you can write the K-map for it. Okay, simplifying the K-map for each of these inputs J3, K3, J2, K2 and J1, K1. Okay, so you see for the K-map, if you'll see, so J3, J1, K1 is, okay, so you see, if I write for J2 and K2, so you can see from this table that J2 and K2, okay, so you see, if K1 and J1 you will directly see, okay, so either in this J1 K1 table, by observation also you can write the equations. So you see, in J1 there is no 0 in this column, okay, so either there is a cross or 1. So you see, if I assume this as don't care and if I pair them together, okay, this whole column, so I will get a 1. So J1 should be connected to 1. Similarly for K1, okay, so K1 there is no 0 in this column, K1 column, so we should connect it directly to 1. Okay, so J1 and K1 will be connected to 1. Whereas what about J2, K2? To find this, we'll write the K-map for J2 and K2 separately, and then for J3 and K3. So if I write the K-map for J2 and K2, then you can see that J2 is this. Okay, so for this J2, you can see that J2 will be equal to Q1. So the output of the first flip-flop will become the input to the second flip-flop. Okay, so this is what it means. Whereas if I write the K-map for Q2 is this. Q2 when you solve it, considering this, so it will become Q1. Okay, so you can see again that J2 is equal to K2 and both of them are Q1. Okay, and similarly on the same lines, if you take the discussion from the previous slide and for J3 and K3, if we write again the K-map, then we find that J3 and K3, okay, will be like this. So J3 will be your Q1, Q2 and K3 will also be Q1, Q2, filling the entries from that table if you make it. So J3, K3 will also be Q1, Q2. Okay, so now after this you can see that this you get this J3, K3 and J2, K2. Okay, whereas J1 and K1 both should be tied permanently to 1. So this is the expression for your up counter. Now let's say you draw the circuit for the down counter. So the down counter is when your M is equal to 0. So when your mod control M is equal to 0, at that time your circuit will count in the reverse direction. So if it is in the 0 state, so it should go to 111 state, then 110, 101, 100, 011, 010, 001, and again 000. Or as the otherwise, if it is in the 11 state, then it should follow this state. So same state. So you draw the state diagram. Excuse. So you draw the state diagram for the down counter, and from this state diagram we write its excitation table. Okay, we write its state table using the excitation table. Okay, so the state table for this counter is, see, present state and next state. So present state is your this Q1, Q2, Q3. So Q1 is your LSB and Q3 is your MSB. The circuit will be same. Okay, circuit will be same means in the same circuit we have to implement both the up counter and down counter. But to simplify the things, first we have designed an up counter and then we are designing the down counter, and later on we will mix them up together. Okay, so that is an important step and that I will discuss later on. So here what I am doing is, present state is this 0 0 0, so the next state is 1 1 1. Okay, for this what should be my excitations, various excitation, J1 K1, J2 K2 and J3 K3. Okay, so that I have to decide. So if I decide this, considering this state table I write, okay, considering the excitation table of the JK flip-flop. Okay, so this is the state table for your this down counter. Now from this state table, if I write the K maps for each of this J1 K1, J2 K2 and J3 K3, then what I get is this. So J1 K1 is easy to understand. It is same as what we have done in our last up counter case. So all of them are either 1 or cross. So J1 and K1 both will be connected to 1 permanently. Okay, whereas J2 and K2, so J2, if you solve it, so J2 will be equal to Q1 bar. Okay, J2 and K2 both will be equal to Q1 bar, whereas J3 and K3 will be equal to Q2 bar and Q1 bar. Okay, so Q2 bar and Q1 bar. So this, if you write, so J3, K3, J2, K2, you get the equation like this. Okay, now you got the equation for up counter as well as for the down counter. Now in the next slide I will show that how to mix them up together, because what we want is, in the same circuit we want up counting as well as down counting. So the only thing which we have to include here is, let's say, a mod control input, which is, let's say, up down count input, you can say. So in both cases we have counted up and down count. Okay, we have to connect, in both the cases we have to connect J1 and K1 to 1 permanently. Okay, so therefore in the up down counter also we have to connect both of them to 1 permanently. Okay, whereas for the up counter you can see that your J2 and K2 should be equal to Q1, and for down counter they should be equal to Q1 bar. So how to include this two? So for the up down counter, what we will do, we have to use a mod control. Okay, M. So M we have used, and we have said that M is equal to 1. When M is equal to 1, our circuit counts in the upward direction. When M is equal to 0, the circuit counts in the downward direction. So what we do is, so for the up down counter we write the expression as J2 is equal to K2, because both of them are same. Okay, J2 here for the up counter, J2 and K2 are same, whereas J2 and K2 are same for the down counter. So we mix them up together like this. So J2 is equal to K2 is equal to Q1 dot, this should be M. Okay, so M is the mod control, so they should be written as Q1 dot M plus Q1 bar dot M bar. Okay, so because for down what we are assuming is our M should be 0, so Q1 dot M, and this should be plus Q1 bar dot M bar. Okay, so this is our down counter. So this is for our up down counter. So if we are mixing, we have designed up counter separately and the down counter separately, and now we are mixing them together. So to mix them together we have used this input. Okay, so M, Q1 dot M, and because you see both of them should be 1, okay, then only this circuit will be 1. So that is why. So Q1 and M plus Q1 bar dot M bar. So our J2 and K2 get this function if we want to make it an up or down counter. Why this is so? Because for mod control this will be activated and this will be deactivated. So this Q1 bar will not become the input to the next flip flop, whereas when m is equal to 1, this q1 will become the input, because we are ending this together and then we are ORing these two terms together. So we are using 3 gates, 2 AND gates, q1 dot m, okay, q1 bar dot m bar, so 2 AND gates, and then those 2 AND gates are ORed together. Okay, so this is what you see, and this is what I'm going to show you in later on. So similarly for the MSB bit, you can see for the up counter we have seen J3 K3 is equal to Q1 dot Q2, whereas for down counter you get Q2 bar Q1 bar, both equal to 1. So here in this case J3 K3 and J2 K2 are same, but you may get something different as well. So whatever expression you get, we have to write it with m and m bar. So m is our up counting and m bar is our down counter. So including them, okay, in an AND gate, if you do, because both of them should be simultaneously 1, then only the circuit should count in the upward direction. And then we OR them together so that we have the optionality that either of them, whenever this particular block gets activated, then the circuit counts in one direction. When the other block gets activated, then the circuit counts in the downward direction. So this is what about your circuit is. So if I show the circuit now, after finding all this expression, I should have included the circuit in the last slide here, okay, but I have included in the first slide. So let me explain this to you. So how this circuit looks like. So you see J1 and K1. So this is our, let me magnify it. Now we can see this circuit clearly. Okay, we have to consider this circuit now. So what I am saying is we are using three flip-flops. It is a 3-bit flip-flop. So J1 is our FF1. Okay, this is our LSB flip-flop, whereas this is our MSB flip-flop. So both of them, J1 and K1, are connected to 1 1 simultaneously. So this is what we have decided. J1 K1 is equal to 1 permanently. Okay, whereas a negative age triggered flip-flop. Okay, so this is negative age. We have bubble we are using to show the negative age, whereas this triangle we are showing to show age. Okay, now this is an this is a mod control we are using, okay, in this circuit. So when m is equal to 1, so we are using m and we are using a NOT gate here. So here if m is equal to 1, then this will be m is equal to 0. Okay, so you see when m is equal to 1, what will happen? This circuit will, this AND gate, this Q1 and this M1 is equal to 1, so this AND gate will be activated, and this output will become the input to the flip-flop, to this flip-flop, and you see that both J2 and K2 should get the same input. So you have connected both of them together and you are feeding it with this OR gate. Okay, now when m is equal to 1, at that time what will happen? M is equal to 1, so this will be activated, whereas this will be deactivated. When m is equal to 0, at that time this circuit will be off because this is an AND gate, so this will not work, whereas when m is equal to 0, this will be 1, so this circuit will get activated. So when m is equal to 0, Q1 bar, okay, with m is equal to 0, so Q1 bar dot m bar will appear here, whereas when m is equal to 1, then at that time Q1 dot m will appear here. So this is what we wanted, so this is how we have to do it. Okay, so just to design this circuit, what should come here, we have done all this process, all these steps we have done just to find this, what should come here. So depending upon the problem or depending upon what is written in the statement, you have to design the circuit. So this circuit we have to find. When we say that we are designing a synchronous counter, so basically we know that we have to use certain flip-flops. So there's number of flip-flops we can decide very easily. We can decide that how the clock pulse will go. So all the clock pulses, all the flip-flops will be triggered simultaneously by a single clock pulse. But then we have to decide this in-between circuitry. To decide this on in-between circuitry, we have done all these steps. What we have written the excitation table of the required flip-flop. Then after that excitation table, from that excitation table we have written the state table for the circuit. Okay, and that state table we used the state diagram to write the state table, and after writing the state table we use the K-map to simplify the expression for each of the input, and after simplifying the expression and whatever we get, then we implement this circuit. Okay, so this is the general procedure for your implementing a synchronous counter. So we have completed this. Okay, so this is how your circuit looks like. Okay, so similarly you can verify it for the other this J3 K3, so J2 K2. Okay, so this we can see, this is J1, this is Q1 and this is Q2. Q1 Q2 are coming, and when m is equal to 1, Okay, so this circuit is activated when this m is equal to 1, whereas this circuit will be activated when m is equal to 0, and this will be q2 bar and this is j2 bar. Okay, q1 bar and q2 bar. So this is coming like this. So this will become the input to the next flip flop. So you understood the procedure. So let us move on to the next thing. Okay, so the next are simple. Okay, so I'll discuss this in the next part of this lecture. So thank you for listening.